Okay, so now we are doing investigating the vertex of a quadratic function. So we're going to be taking a look at the vertex. We'll talk about what the axis of symmetry is. We're going to interpret parts of the quadratic function in terms of a problem situation, which we've done before. And we're going to use the calculator to determine the x-intercepts, the y-intercept, absolute max or min of a quadratic function. We're going to solve it graphically. Well, I hate this word here because a function is not solved, right? A function is just a tool. We've talked about that before, how you don't solve a fraction bar, right? So we're not going to solve a function either, okay? But we can see what it looks like, and we can solve for zeros. A lot of times I think that's what they mean is find the zeros, right? So we can maybe do that. Or solve some kind of problem that is related to a quadratic function. Now we're going to find the vertex of a quadratic function. We're going to use symmetric points to determine the location of the vertex of a parabola. And we're going to use the vertex to determine symmetric points on a parabola. Okay, so this will be kind of interesting here. I'm going to skip forward. We're talking about launching a pumpkin by a catapult. So I want to draw this out a little bit, okay? If you've ever seen or heard about people doing this, but they build themselves a catapult. Okay, so it's on a wheels, I'm going to say. I don't know if this is a catapult or a trebuchet or what it's called, but you have some kind of a device, right? And back here at the end of it, here is the pumpkin, right? Okay, and then there's some kind of ropes or something holding it down, right? You got some kind of spring wanting to push it forward, so it wants to go forward. And then when you release this, right, either cut it or there's a trigger to release it, then of course that pumpkin is going to go flying in the air, right? It's going to fly forward and we're going to land somewhere over here, right? So now the key is to think about that there's a bunch of different motion going on here, right? The pumpkin is going up and then the pumpkin is going down. So we have an increasing value of its height, and then eventually a decreasing value of its height. And of course, at the highest point, then that would be called the vertex, right? So we've talked about vertical motion already and using the vertical motion model, right? And here it is again, right, where we're going negative 16t squared, and t is time in seconds, v0 of t. So v0 of t is the initial velocity or speed. You can think about it as the speed of the pumpkin when it launches at the time of launch, right? The initial velocity right here. And then we have this initial height of the pumpkin. We think about how high is it off the ground, okay? So it says, why do you think it makes sense that the situation is modeled by a quadratic function? Okay, well, let's think about this. So we have height measured over here, right, on the y-axis. And then we have over here on this x-axis, we have time. So at some point, that object is on the ground or very close to the ground. But then as time begins with this little experiment, we release that pumpkin into there. It's going to go up for a long time, and it's going to get to a point it's going to slow down. And then what's going to happen is it's going to start to fall. And it'll fall a little faster and faster and faster. And what is the shape we end up with? Not very well drawn by me, but you should see, that's clearly a parabola. So why do you think it makes sense this situation is modeled by a quadratic function? Well, there is a parabolic motion when we consider these two factors, the vertical height, how high up in the air it is, over time, right? Now, this is really important because we're talking about vertical height and vertical velocity. This, even though it looks like that, because that pumpkin is moving forward, up, and down at the same time, this is not measuring forward. This is just measuring time. And as time goes on, the pumpkin goes up in the air, and eventually the pumpkin comes down. We don't know where, because this is only measuring vertical motion. Right? Vertical motion, not horizontal motion, not some motion forward in space, okay? So now it says, suppose that a catapult hurls a pumpkin from a height of 68 feet. Okay, so it starts the pumpkin out at a height of 68 feet. So maybe it's up on a platform somewhere. So the initial height, that's this number here, we're going to put in as 68, right? And then the initial vertical velocity, so that's the speed at which it's traveling upward, is going to be 128. So that's going to go here. We're going to put 128, but don't forget to put the t, right? And if you're graphing this, like I'm sure we will here in a minute, we're going to graph it as 128x. So we have positive, and that's a positive 128. T, or soon will be x. We'll consider it x. Okay. Now it says write the function for the height of the pumpkin h of t in terms of time t. So you would have h of t is equal to negative 16t squared plus 128t plus 68, right? Okay. Now it says, does the function you wrote have an absolute minimum or an absolute maximum? And how can you tell? So remember, we can always look at this value a right up here in front of our t squared. This value a, since it is negative, tells me that we have a function that opens downward. And when it opens downward, that means there is eventually some maximum height. And it goes up and it reaches a maximum height and it comes back down. And it opens down, right? So it opens down from a maximum height. So this one clearly has an absolute maximum, which we can tell because of that negative value here, right? All right. Now it says graphing it. Graph it using the bounds, -19 and 0, 500. Okay, and those are inclusive. See the square brackets? The square brackets, okay. And so I'm going to go over here. Oh, wrong place. And we're going to put this in here. So y, I'm using y, of course, but we're putting negative 16x squared plus 168x plus, wait, what was it? Wait, it was 128, sorry. It had an initial velocity of 128, and then it was on a platform at 68 feet. So this has to be 128, right, plus 68. And we hit enter, okay? And now let's zoom out a little bit. They actually want us to set, I don't know if I know how to do this, set the, let me see if I can, no, that's not going to work. Can I set the, let's see if I can, graph settings. Okay, on my x-axis. Okay, good. So there's the, they want me to use these for my domain. This is the interval for the domain, the x-axis. This is the interval for the range, the y-axis. So x-min, x-max, y-min, y-max. So we're going to go -1. So -1 to, I think it was +9. Yeah, +9. And on the y-axis, we're going to go from 0 to 500. So we go over here, make that 0, and then make this 500. And I think in this book, when they tell us to do this, okay, and we can go ahead and click off to the side. And what I don't really like is because I always would go a little bit lower, right? We want to see those zeros, so I'm dragging it upward from here. But basically, now we have a nice view. You can see that, you know, the pumpkin didn't start out on the ground. The pumpkin started out over here, right? At 68 feet in the air. Then it went up, got to its highest point up here. Right, once it reached its highest point, that was nice. Then it came down here and it hit the ground over here, is where it landed on the ground after, what, 8.5 seconds, something like that. It looks like about 8.5 seconds. Hit the ground. And how high in the air did it go? Well, the vertex is somewhere around here. This looks like this is 20, 220, right? These are counting at 20, so 320. Somewhere around maybe 325 feet or something like that, 323 feet, something like that. And again, this is not what I am used to seeing. I clicked on it and there it is. So now you can see at 4 seconds, there's my vertex. At 4 seconds, it reached 324 feet in height. And it hit the ground out here at 8.5 seconds. And there it was at 68 seconds. And had it started on the ground, you would have had to start at -5 seconds. You had to launch it up, okay? All right. Now it says graph the function, so you should be able to graph that. Using a graph calculator, or use a graphing calculator to determine the zeros of the function. So what are the zeros? The zeros are, the zeros are these points here on the graph. In this problem situation, this is when the pumpkin hit the ground. Okay, and the other zero over here, this is when the pumpkin would have had to leave, the ground in order to stay on this same arc. Okay, all right, so determine the y-intercept, to interpret its meaning. So y-intercept, wait, this is easy to see, because see, if all this went away, if all this was 0, this would be my y-intercept. In other words, when x is 0, right, then I put 0 in here, and this all turns into 0. And I put 0 in here, and this turns into 0, because 128 times 0 is 0. And negative 16 times 0, 0 is 0, right? I mean, all this becomes 0, and when you add 0, what's left? Nothing but 68. So this is clearly when x is 0, y is 68, and I can see it right here. There, it's right there. So what does that mean, the y-intercept? The y-intercept is the height that the pumpkin was at the moment it was launched from the catapult, right? Right when the launch began. It is the initial height, okay? And then determine the graphic calculator, determine the absolute minimum or maximum. In this case, it's a maximum. Explain what it means. So the absolute maximum we found was right here at 4,324, which means 4 seconds after launch, right? 4 seconds after launch, it reached the highest point vertically. That pumpkin was 324 feet in the air. Man, that is very high, okay? All right, so the vertex of a parabola is the lowest or highest point on the curve. The axis of symmetry of a parabola is the vertical line that passes through the vertex and divides the parabola into two mirror images, which is really cool about parabolas, right? Because they can be divided right down the middle, and you would have exactly on one side, you'd have exactly the same thing on the other. So this is because the axis of symmetry always divides the parabola into two mirror images, you can say that a parabola is symmetric, okay? You have been calling the lowest or highest point on a parabola an absolute minimum or maximum. Now you know that this point has a special name, the vertex, okay? It says now, because a vertex is symmetric, over which line would you fold it to show its symmetry? What is the equation of that line? So let me draw that out for you, this line. Ready? If I was going to fold this over on itself, right, I would need to fold it from that point right here, right? Straight down right here. And what is the equation of this line? That's what they're asking, right? This is the equation line. It goes through the vertex. Oh man, I'm not drawing that very well. Sorry. Goes through the vertex and it's straight up and down right here. And I could fold this over and it would be exactly there. And where would I need to fold this? I would have to take my, if this was graph paper, take my paper and I'd fold it over and I would make a crease right here at what number? I'd make a crease at x equals 4, wouldn't I? That's where I would make my crease or my line of symmetry at x equals 4. I wouldn't do it at y equals 4. That's over here somewhere, right? Go up to y equals 4 and draw it. That would not be symmetrical, right? It has to be, I'm drawing this line right here where x is equal to 4. That's where I'm going to fold my paper or draw my line. So x equals 4 is my equation. Oops. Oh, we're going to go back in there. And that's be what I'd write here, right? I'd write the equation of that line. That equation of that line of symmetry is going to be x equals 4, right? And now it says, remember the pumpkin chunkin scenario in which you wrote the function, blah, blah, blah. Okay, identify the coordinates of the vertex of the graph and the equation for the axis of symmetry. So the vertex was at 4, 324, right? And then, oops, that was the coordinates of the vertex. And now the equation for the axis of symmetry, that was at x equals 4, right? That's where I would fold that. And it says, use a graphing calculator, answer each question. When does the pumpkin reach a height of 128 feet? Aha! Tricky. So using this calculator, it's kind of, you guys know how to trace and stuff, right? But using this calculator, it might be hard for me to see that. I don't know how to do a trace on this. Oh, look, I can click and drag. So if I'm tracing, I'm just looking for what feet? 128 feet. So I could go like this until that says 128, right? And I can see it. But man, that is even hard to do. And then go up to 180 or whatever. I got another way. What if I do this? What if I just go y equals 128, and now I can see the point where they intersect, right? If I have two functions or two equations and it shows me the point, I find the intersection point. That tells me that it reaches 128 when x equals 0.5. You see that 0.5? 0.5, so be a half second. That'd be 0.5 seconds, right? And when does it reach 180? Well, that's easy enough to do, because look what I'll do. X equals 180, and now what do I have? At 1 second. So 1 second. What about 308? Well, no problem. 308. And then here we have it. It's hitting at 3 seconds. But notice, hey, wait a minute. It's also at 308 over here at 5 seconds. So 3 and 5. So my answers here have to be 3 and 5 seconds. What about this one? What about when we said 180? Let's try that again. 180. So when was that? Ah, look. This was at 1 second, and then over here at 7 seconds. So 1 and 7. Huh. And then, what did we have? 128. 128. That we said was at a half a second and 7.5 seconds. Aha. Something interesting about that, right? Something interesting about how far is this from 4, from the line of symmetry? That's 3.5 seconds away. And this to 7.5, that's 3.5 seconds later, right? Think about that. What about when I put in 180? Well, check this out, right? Here's the line of symmetry at 4. So it hits this point at 1. That's 3 seconds away. So when's it going to hit that other point? 3 seconds away from 4 is 5, 6, 7, right? And then we had 308. Was that right? 308. 308. Oops. Not going to hit anything there. 308. And I see, hey, that's 1 second away from 4. 3 is 1 second away from 4. So what will this be? 1 second away from 4 also? Because it's symmetrical, right? 5. So the line of symmetry, right? Every time we're looking at any point on the graph, it's always equidistant from the line of symmetry. Well, you think that works with the zeros? Of course, yeah, right? This is what? 4.5 seconds away from 4. And this is also 4, look, 2, 4.5 seconds away from 4. So the zeros are also equidistant from the line of symmetry. Well, that's kind of interesting, because now if I know my zeros, I can find the midpoint right in between those zeros, and I can draw the line of symmetry, and I can tell where my absolute maximum should be, up here, right? So if I didn't know for sure, but I knew this was a 0 here at 8.5, and this was a 0 here at -0.5, and I said, hey, what's halfway between them? 4. Then I could go in here and I could say, okay, well, where does x equal, where does x equal 4? And draw my line of symmetry, and boom, there's my vertex. Oh, it hits there at 324. Now, I don't know that this is my vertex yet, but it makes sense, right? Because this is exactly my line of symmetry. It cannot be higher on one side or the other. It's got to be high just in the middle, okay? All right, number 4. So they want you to construct the graph, right? Plot and label the vertex. Draw and label the axis of symmetry. Plot and label the points that correspond to the answers. Plot and label the points symmetric to the points from part B. Plot and label the zeros. Okay, you can do all that. We just graphed it out together. What do you notice about the y coordinates? Okay, what do you notice? Analyze those symmetric points at 128 and 180 and 308. What did you notice? Okay, they are symmetric, right? They are equidistant from the axis of symmetry 4. What do you notice about each point's horizontal distance from the axis of symmetry? They are equidistant from the axis of symmetry, right? And how does the x-coordinate of each symmetric point compare to the x-coordinate of the vertex? Well, each x value was exactly the same distance away from the vertex, right? Or from the vertex. A vertex had an x value of 4, and when we did 308, one was at 3 and one was at 5. They were each equidistant from 4, right? 1 second away, 1 second before, 1 second after, right? All right, and that's because we have them being symmetrical. So use the given information to answer each question. Do not use a graphing calculator. So how am I going to find the axis of symmetry for this parabola? If the x-intercepts are at 1 and 5, and I've got to find the line that is right in between 1 and 5. Right in between 1 and 5. All right, well, let's go in here a little ways. If I had a line here at 1, let's just go x equals, let's change this out, x equals 1, and then I had another one here at x equals 5. So here we go. What's the point right in between? Aha! So the axis of symmetry would have to be at x equals 3. How about negative 3.5 and 4.1? Well, I'm going to leave that for you to figure out, right? How far apart are they? Well, actually, let me help you a little bit with this one, right? How do we figure out how far apart things are? You take the bigger number and you subtract the smaller number, right? So if I want to know how far away 12 is from 8, I go 12 minus 8. So here I'd have to do that. So I'd go 4.1 minus negative 3.5. What happens when I go minus a negative? Turns into plus, right? So 4.1 plus 3.5, which turns into 7.6. And then I divide that in half to find the halfway point, and that'd be 3.8. So it has to be 3.8 away from this, and has to be 3.8 away from that. All right, let's try this and see if we can come up with a little bit of a formula on this. Watch this. We take this value, right? We take the larger value. So let me write here. We're going to use this. So we'll call this lesser value, the smaller 0. We'll call it x1. And here's the larger x-intercept or 0 at x2. So we're going to take x2 and we're going to subtract x1. That's going to give us the total distance, right, between the two. And then we're going to divide that in half, and that's going to tell me what half the distance is. And then I'm going to take this value and I'm going to subtract it from x2. So if I go x2, this will be my little formula. Watch this. x2 minus x2 minus x1 over 2. So let's think about how this would work out. Why don't we try it with a simple one first? We got a different color in here, and let's see what we do. So x2 would have to be 5, so I'd put 5 here, right? Minus, and then I'd put 1 here. So 5 minus 1 is 4, right? So this whole thing would turn into a big old 4. But then I'd divide it by 2, so this whole thing would turn into a huge 2, right? So I end up with x2 minus 2, right? Well, x2 was 5, so I'd go 5 minus 2. What does that equal to? That's equal to 3. And so my x equals 3 would be my line of symmetry. Why? The whole distance between the two is 4. Halfway would be 2. So halfway, 2 away from this x2 number, that would give me 3. Ooh, boy. So let's see if I can go back in here. Oh. And there it is. 5, take away 2, right? The whole distance is 4, divided in half, and I get 2. So 5 take away 2 gave me 3, and that would be my axis of symmetry, right? If these were my zeros. All right? So the same thing is going to work for you when you do this, okay, and when you do that. Go back and look at that formula, and then you can describe how you do it. And then, oh man, if you know that this is a totally different one. Let's see, how much more do we have? We have a few in here. Actually, you know what? This is probably good enough for today. We're going to stop there, but I will tell you this. If you're going to have to find the location of the vertex, and you know the axis of symmetry is at -2, you think about it, you would have that parabola, you would draw -2, right? That'd be your line you're going to fold, x equals -2. You'd fold the paper there, you'd go up or down until you found the value of the parabola at -2. So you would want to take and put -2 inside for x. So you're really trying to find out what is the value of the function when x equals -2, right? And to do that, you're going to have to take -2 and square it. That's going to be +4. And then add 4 times -2. So we're adding 4 times -2, right? And then we're adding 3. All right, so -2 squared would be +4, right? And 4 times -2 is -8, so 4 minus 8, right? That is -5, and then plus 3. Sorry, 4 minus 8 is -4, and we add 3, right? So this becomes -4. Oops, like that. That's -4. Then we add 3. We get -1. So the value of the function f at -2 is equal to, these should be parentheses, I'm sorry, not absolute values. So it is equal to -1. So what does that tell me? The vertex, right, which is on -2, because it's on the axis of symmetry, the vertex is at, here's the vertex. The vertex has to be at -2 for x and -1. What does that also tell me? If I have zeros, right, then what would have to happen? This has to open up because my vertex is below the x-axis, right? -2 would, here's the y, and here's -1, and -2, and here's -1. So my vertex is here, so it has to open up from there. Actually, it doesn't have to, right? Maybe it doesn't have any zeros. I don't know. But if we look here, we can see that a is a positive number, right? There's no negative sign in front of that x squared, and that means we're going to be opening up. Okay, that's definitely enough for today. Hope you learned something good.